My name is Scott Moulton. I run two companies side by side, a forensics company called Forensic Strategy Services and myharddrivedied.com. Some of you, if you've done any kind of research or anything on forensics or data recovery, I have like 80 or 90 hours of do-it-yourself, how to rebuild hard drives, repair boards, do those kind of things. None of them are fluff. They're all the real thing. So it's not like, oh, well, you know, here's what you can do, and then send the board to me, and I'll fix it for, you know, a fee or whatever. I kind of work from that hacker mentality of information, or as much as I can do, should be free. Let's try to get it done as much as possible. Not that I don't want to earn a living. So if you want me to work on stuff, I'll take a paycheck. So I have a lot of nice animations. My content is primarily about the solid state stuff. I've been doing work on solid state drives, not only in data recovery, but also in forensics cases since 2005 and 2006. So some of the first renditions of solid state drives, which kind of drove me to do some research and do some other items. I could talk about all the things that I do, all the, you know, nobody cares really, blah, blah, blah. You really want to know this information, so I'm going to get right to that. The only thing I can tell you otherwise that anybody might care about is that in Vancouver in December 5th to December 9th, I teach a class. Some of you may have heard of the SANS Forensics Hard Drive Data Recovery course, SEC 606. And Forensics 606, I wrote that class, which I also teach on my own. So on December 5th through 9th, I'm teaching in Vancouver. If anybody cares, go to myharddrivedied.com. Otherwise, hang on if you have any questions. You can kind of blurt them out. I can only go forward. I can't go backwards. So the animations only go forward. So if you're going to say something, say it quick. I have a lot of information, and I will jam-pack it at the end. Maybe if we have some questions in that last 10 minutes, let's get that in, but feel free to ask. The big disclaimer that I have here is that hard drive manufacturers, and I pretty much know everything that there is from a hard drive perspective. I've been doing data recovery for 11 years, almost 12 years now, and I've dealt with just about every type of hard drive, platter assembly. We are a physical data recovery shop, so we actually do the platter reassembly, the head reassembly, the firmware reassembly, board repair, infrared soldering, desoldering, all those things. So I pretty much have all of that worked out, so anything you want to know, I've got that down. In the last 30 years, hard drives basically have merged together. We're down to only 3 manufacturers left. So we got Seagate, Western Digital, and Toshiba, basically. Everybody else has been purchased. They are all going to either disappear. You're not going to see Hitachi's on the shelves. You're not going to see Samsung, unless, you know, they're still using the name just because of OEM stuff or whatever else. But they've all been purchased by everybody else. Almost every hard drive at this point looks identical. When you're opening them up, about the only thing that's really different, you know, they can have a head that goes one direction or a head that goes another direction or a certain number of heads, but fundamentally, the firmware is basically the only thing that's really different. Most of this stuff works exactly the same from one drive to another. And we've got 20 years of reverse engineering material that's been published and released and equipment that we can work on hard drives. This is not the case with solid state. Solid state now is in its 4th and 5th generation of content. They are all about intellectual property. Everybody wants to be the leader. They want to license their material to someone else. So when you're looking at something made by SanDisk, they want to own the market. Everybody wants to own the market. So we're at the cusp of this new beginning where nobody's got any material, and they are generating new versions of solid-state drives very rapidly now. So you're looking at, you know, 3 and 6 month cycles. We don't have enough time to reverse engineer this process to actually fix it, and things have been changing along the way. So what we could do 2 and 3 years ago with solid-state drives for repairing them or reading the NAND as a raw device like we do with hard drives, we cannot really do conveniently anymore on current solid-state hard drives. And it has a lot to do with encryption and compression and all these other things. So I just want you to know that basically what my talk is about is the things that are the same as much as possible, and then the complications, and then comparing those from a forensic standpoint and a data recovery standpoint to what actually happens with hard drives and what you're looking at that's different. So what is a solid-state hard drive? So basically, a solid-state drive. Solid-state drive itself is one of these terms that's been mutilated, a lot like a router or a gateway and those kind of things. Things that used to be different that are no longer different. Solid-state basically means I have no moving parts. And so I'm reading and writing to something that has no moving parts. But when you actually say solid-state disk now, there's, you know, people are trying to say that there's a definition, and this is what this means. And in most cases, what you're looking at is the fact that the device has to emulate IDE or SATA in order to communicate with ATA commands. That's really what they mean when they say I've got a solid-state disk. But a USB thumb drive is a solid-state disk, right? It's a solid-state drive at this point, but basically it does not have any way to communicate with the system through its own processor or emulate ID. We actually had to make modifications to the BIOS in order to actually make these things boot, or to do something with them from the system's perspective, whereas with a solid-state drive, you do not have to do that. It has its own processor, it is a discrete controller, and it is in charge of what is actually happening to its data, and it does answer to most, if not all, ATA commands. They did not implement the full ATA command set. I'll talk about that in a little bit. So, forgive my jokes here. It works well in front of 3,000 people. So. Every presentation I do, she's always pissed at him. So a hard drive, if this laptop had a standing hard drive in it, basically this standard hard drive, as it hits the ground, regardless of what IBM shows you, with a ball and crane swinging through and hitting the laptop, or Toshiba's, impact-resistant zombie hard drive that they talk about, or whatever. If it falls far enough, you're going to have damage to it. You're going to have a head assembly that's going to whack a platter. And really, to be honest with you, what this magic is, where people always talk about this head assembly being parked in the ramp and it won't slide out and do damage to your drive, blah, 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 is all a piece of plastic that works on airflow. Basically, almost every single hard drive has a little tiny piece of plastic down here at the end of the actuator arm that moves out of the way when the platters spin up. It waits for air pressure, and then it teeters out of the way, and then the head assembly can move. That's really all that's protecting your disk. There's not a lot more to it than that. And so there's not a lot of activity or motion. There's no power. So these things can still happen. So what if it was an SSD in this? So this is my rendition of a Wayback Machine. Now it has an SSD drive in it. So this is a party on a chip. So this thing is still moving. It's doing great. We got a disco ball, so everybody's happy. Unless when the thing hit the ground, you had a crack across the board or something along those lines, because there's no moving parts, it's more likely that your content is going to survive than it is going to be on a disk. And then, of course, he has what you all get to investigate. So other reasons, this is the very short, fluffy session of my solid-state stuff. The first thing is that hard drives, the reading and writing reliability is supposedly improved when you're looking at what you're going to use a solid-state for and why you would use it over a hard drive. So this is where people kind of been taught wrong for 20 years or whatever. A hard drive does not have zeros and ones on it. There's no zeros and ones. It is basically something like a waveform that is encoded. It's actually very analog in nature and has an encoder and a decoder and modulates the data, runs it through a read-solemn encoding pattern in order to nullify and randomize some of the content. And I'll show you what a sector actually looks like later, because it doesn't look anything like what you're used to. But basically, when you're talking about reliability, you're actually looking at the fact that you're actually having to decode a lot of content. There's a lot of errors that actually occur all the time. The head has to reread numbers of sectors, and if it can actually compensate for it with ECC, it just does. It doesn't even argue with it at all or go back and read the sector again. So if it reads it, fine in the second or third pass, forget how many. As long as it's, less than 10 or whatever the threshold is by the vendor, it's still going to count that as a read. Whereas on solid-state drives, you actually have something that's much more, it's still analog. There's really no such thing technically as the digital circuit in this case. It's basically an amount of electrons that are charging a cell. And then if it's over a certain amount, so for example, let's say we can store 600 electrons in a cell, and at 300 electrons, it'll create a charged value, and that charged value will be high enough to interpret that as a 0 or a 1. And that's basically where we get a 0 and a 1 from. But it is more symbolic of a 0 and 1 in a solid-state drive than it is in a hard drive. So that's the first thing. The second thing is speed. So people talk a lot about how much faster solid-state drives are than hard drives. And there is some truth to that, but some of it has been increased because of caching and their ability to actually cache content in a solid-state drive even, as opposed to what they're actually doing in a hard drive. Now, on a hard drive, people talk about the outside edge of a disk being faster than the inside edge of a disk. And technically, that's not true. It spins at the same speed all the time, so you have constant angular velocity, and it's always spinning at the same speed. But what you have is on the outside edge of the platter, where the lowest LBA numbers, logical block addresses, are, you have more sectors at that location without moving your head. So your head assembly is sitting in one location, and there is no latency for that head to move from one place to another. It can stay there and read more content. So you have a lot more content being read at the same time on the outside edge as opposed to the inside edge of the disk. So as it's moving, you also have another thing, which is there's data stored on other platters. All of these heads, it's a myth that the heads all work together at the same time. They're all moving together, but they don't work together at the same time. Only one head on a hard drive can be on at a time. So you have to turn it on and turn it off, and turn on another one, and turn it on and off, and so on, all the way down through the stack. Data is not stored in a stack. Now, at least pretty much since 1998 and 1999, data is stored in what's similar to little tiny football fields all over the top of each platter. It's actually contiguous data so that they do not have a latency with reading content from the platter itself. So they'll actually have what's called a zone table, a zone map, and they'll store contiguous data. So it's possible to have damage on the lower side of this platter, but still have 2 gigs of contiguous data where all your Word documents are on the top platter. So that can, in theory, happen. Whereas over here on a solid-state drive, if you have a major death, in a lot of cases, the actual drive won't respond at all. You'll actually have a lot of difficulty actually finding something. You can't pull one chip off and hope that you're going to be able to read the rest of the data. That's not going to happen. So we'll talk about why. Power consumption, you'll see, Tom's Hardware has arguments about this every week. But let's face it, a spinning disk has a motor, and when you have to spin it up, you're going to use more power than you're going to use going from a state of idle to in use. And so typically you're looking at less power that's required for it to stay active and contain that material. You have no noise and vibration by comparison. That's pretty nice. Temperature is extremely different between the two devices. Not that a solid-state drive is all icy cold over here or anything, but and for people who don't recognize it, that's a MacBook over there on the left. Those things, don't put it near your gonads. The weight is certainly different. There's not much argument that plastic weighs a lot less than metal does. So let's talk about the types of solid-state drives that exist. DRAM is the first one. This one has actually existed for like 30 or 40 years. It is a solid-state drive. This is what you'll see in your rack mount systems at like Wachovia or banking systems and things like that, where they got to do hundreds of thousands of transactions a second. The DRAM is basically the same RAM that's in your computer. And it is 300 or 400 times faster than even our current solid-state hard drives. Even the fastest solid-state hard drives that we have, the NAND cannot communicate anywhere near as fast as DRAM. But obviously, turn off power, you lose your data. So they have come up with something very similar to hibernation. Basically, these are very similar to what we do in the computer, where when power goes out, you have a certain amount of time before it's going to shut down. It'll freeze what it's doing, hibernate the file, and then restore it. So these things are great for speed and for doing very little damage. These things will last years and years and years, as opposed to what you actually have with solid-state drives that do damage as they write to them. You don't have that kind of damage happening on a DRAM device. But those aren't very easy to fit in your pocket or take with you on your laptop. So that's not primarily what we're using. The other two are called NOR and NAND, and those are based on mathematical functions and grids, how the grid was actually designed. And I'll show you some pictures towards the end of how the grid's designed and why it's called NOR and NAND, but they're basically mathematical functions. They're both invented by the same guy, Dr. Fuji Masusuka. I always pronounce that wrong, so if somebody wants to correct me, feel free. But he created both of these. He worked at Toshiba at the time. Basically, NOR is something that you know of similar to what you would have in the BIOS of your computer. So back in 1986, which he created both of these in 1984. So they're really not new. We're looking at 94 to 96 before things are being released. So you're looking at a 30-year time period that these things have existed. And we're just now starting to kind of get to use them, mainly because of cost. As cost plummets and you have increased momentum, then you're starting to use them in newer devices. And so basically over the last 10 years, we've been using thumb drives and we've been using solid-state drives, and we change them out as we get bigger and bigger chips. But NOR is a type of chip that can only be written about 10 times before it dies. So it's got a very high rate of read, a very slow rate of write. So it's great for embedded devices like motherboards and things like that. So when you remember back in the old days, you get their floppy out and you'd flash your BIOS on your motherboard, and it would read the old copy and put it on the disk, and then it'd write back the other one, and it's like the reading the copy was like that. But writing that copy was 20 minutes before they actually had it done or whatever. Those things basically will die after you've written them 10 times, so they're great if you have a very limited number. NAND, though, is what we've been using for our solid-state drives and our USB thumb drives and things like that. This is what we know of as flash. And this type of memory basically has a lifespan. You can basically write the older versions about 100,000 times before they die. They have a slower rate of write than they do of read, but not phenomenally different like there was in NOR, which was a much more affordable chip. But those are the ones we're going to talk about. Now, I try to do something that makes things a little bit simpler than they are, and if you look at the electrical diagrams basically for what a gate looks like, you can see it's a little more complicated. So if you really want to know what it looks like, go look up a gate. This is my symbolic version of what's actually happening. This is a paint can, and in the paint can we have a cover that's basically saran wrap. And we have a floating gate at the top and a transistor at the bottom. And what's going to happen is we're going to charge through the oxide layer down into the paint can. The electrons are going to go through a process called hot electron injection. They're going to be shoved into the container, and then the transistor can basically read how many electrons are if you have a charge in there. And I want you to notice that here at this time, the cell, each individual cell, will start empty at a state of 1, which is exactly the opposite of what most programmers are used to. It is empty, it is 1. When we have a charged value, we then have 0. And this is how we will begin with something called an SLC, which is basically a single layer chip. Basically, you have a single layer that is actually going to be charged, and we're going to count this as either a 0 or a 1. And so as we charge this with the hot electron injection function, we'll actually inject electrons into it. Now, I know I only have one, big electron jumping around in there, but it's actually many. There'll be a large count of them in there depending upon what type of NAND was chosen. So when the cell is actually charged, as an example, let's just say what I said earlier, that there's a charged value that could be as high as 600. And at 300, we're going to call it charged, and therefore we will now have it be in a state of 0. So as soon as we have 300 electrons or more in there, it now has a charged value. That's just an example. It's not exactly. You have to go look it up. But fundamentally, that's how it works. So as we go forward, we're actually going to count that as that state. Now, write endurance is how many times can we do this? Basically, this process of injecting it, we are basically charging it and injecting it. And this process does some damage, and the process by which we erase it also does some damage. So the erasure process, when we have to release content from here, we basically have to open up the gate and allow the electrons to escape. And in that process, it will actually do damage. And so eventually, it will die, and you will not be able to charge this value anymore at all. When it does, the device just removes it from access. It will basically be called a bad block at that point, or a bad sector at that point. But as you're reading and writing to it, as I said, you could do 100,000 writes. That sounds like a lot until you're looking at how many times does a FAT table update in a day, or an NTFS table update in a day with a date and time. It may be thousands already. So typically you're looking at about 18 days of lifespan if you were to constantly just allow your operating system to live on one of these. 18 days, that's about it. So the process that allows it to live longer is actually software. Software is running, doing something called wear leveling to kind of increase the time. It doesn't actually increase its the location's ability to store more. It just stores data in other locations so that you're not reading and writing to the same spot over and over and over again. And if that's the case, when you're actually looking at constant reads and writes with the software, this was a function called ReadyBoost. If you guys remember, Vista had this function in it called ReadyBoost, and the theory was, well, you don't have to add memory to your computer anymore. You can just put in a memory stick in your USB slot, and it would write the page file there, and it'd be faster, which I don't think anybody ever had a test that actually showed that it was faster, because I don't think it was faster. But either way, the page file itself had a limited size. It would basically live for about 3 years if it had constant reads and writes on this device all the time. And then depending on how large this was afterwards, that's what you're looking at as far as lifespan. Now, nobody would probably use a USB memory stick that long because, well, the newer and better one comes out next year, and all of us upgrade right away. But this is actually a quote that came off a manufacturer's page who sold the NANDs. Basically, NAND itself is a chip that all the manufacturers will buy from the same handful of sources. There's only a handful of sources that actually make NAND and sell NAND, and everybody uses it. And then what's different is their software. So in this particular case, when flash memory wafers are tested and probed, a distribution of bad, weak, and strong dies are identified across the wafer. Bad cells are marked. The remaining cells are sorted into consumer industrial quality flash, and then the consumer grade flashes make it into the disks that are mass marketed through retail chains. For people who don't understand what that means, it means they're selling you the crap. The junk that doesn't work, the stuff that failed, that's what you're getting at Fry's or Micro Center, Best Buy, or whatever stores you have down the street. The good stuff goes to, say, Cisco or something like that they're using in their routers, which, rightly so, it's a lot better that you should have a router that works than your USB memory stick. But basically, you're getting the crap off the shelf. The other good stuff is being sold to somebody else. And this is probably no different than any other industry. Intel does this with processors and everything else, but basically, you're getting the junk. So let's talk about one of the other things that is a trend that basically has taken over, and that's called MLCs. So when we're talking about basically anything before 2007, 2008, it was all SLC. And SLC is a very fast single-layer chip. It either has a 0 and 1 in its cells, and you can determine it fairly quickly and fairly easily. When they decided that, hey, we would like to store more and increase the density of our chips so we can store twice as much, why don't we come up with a method that allows us to have a new numerical calculation off of a single cell? Now, it does not actually look like this. This would make sense if they made it as 2 paint cans on top of each other or 2 cells on top of each other. It's not. It is one single paint can, and that content is basically charged with more electrons. So what you would say is, well, my thing used to be able to say I only had 600 electrons, but maybe we're going to increase the charge value. So now at 300, I have one value. At 600, I have a different value. At 900, I have a different value. And we're going to charge it more. So this process of hot electron injection does more damage. It actually will hurt the cells a lot more, exponentially, a factor of 10. So what you're looking at this point is if you charge it and you store twice as much data in the cell, you now have decreased your speed by 40%, but you have increased the death of this cell. And instead of writing 100,000 times, you can only write 10,000 times. So as you go from a 16 gig chip to a 32 gig chip, that's what you're looking at. A chip that as it gets bigger actually is worse. It actually lives a shorter period of time. We also have another one that followed this one called a triple bit. 3 times the amount is then stored in there, which, as you can imagine, does more damage and decreases the speed again. And triple bits are what you get when you get a 64 gig chip or something along those lines. And those you can only write to 5,000 times before the cell dies. That's a tremendous difference from an SLC where you can write 100,000. So our drives are getting worse. So in order to compensate for this, they actually are putting more and more cache on a device so that you have more cache and it's being stored there before it needs to be written, and you can try to keep it alive as long as possible. But of course, as you know, if you lose power, then you start having more and more problems with your data as well. So just know that there are multiple versions of this, and doing engineering, it makes a big difference. So we're going to go back to SLC. We're going to talk about everything as an SLC because it all looks like SLC. It doesn't look like MLC or triple bit. There is a bigger grid, and I can show you a picture of what that actually looks like. We still have a byte like we've always had, but we have something else. It's called the word line. A lot of programmers are used to dealing with words, and in this particular case, that's actually how the grid works. The grid actually writes a word at a time. So in hardware, it actually has to write a physical word. So that is actually why a word line actually matters, and you'll see most of the definitions dividing it up into word lines. We still have a sector. However, sector has changed. What we knew of as a sector, which on most hard drives is 512 bytes, up until just recently, every hard drive had a sector that was 512 bytes. You could vary a sector, like for instance an AS400. An AS400's SCSI hard drive can be changed so that it actually stores 522 bytes. But generally speaking, we're used to seeing 512 bytes. We have new Western Digital drives that have changed the sector to 4K. It still delivers to you 512 bytes logically, but to the device now, it actually stores the content in 4K. Everybody familiar? Anybody seen these drives? You have, you just don't know you have. You probably have some because all they did was change the label to say advanced format. That's what it says. If you are using these drives with advanced format in Windows XP, you have a problem. You need to know about this, and you need to do some research on it, because in XP, it can't compensate for what's called a cylinder boundary. You have a existing problem that has existed, and again, this is about solid state, but just to make sure everybody's clear and has a little nugget when you leave here, a hard drive back in 1982, it was very time consuming for you to turn off a head and turn on a head to go search for your partition structure. So what they decided to do, and it's a definition in FDisk from 1982 until Vista, you had to have a partition begin on a cylinder boundary. So you would actually know that if you had two partitions, that there's a small gap in between the partitions, and there's always this partition gap that people talk about in forensics about how to go and gather this data. Well, that's because you can't start the beginning of the next partition till you actually have the beginning of the cylinder boundary. So you actually have a numerical value that has to be reduplicated, because we always put heads in geometry on the same side of the platter to search for the beginning of the cylinder boundary. If nobody really gets that, then ask me afterwards. I've got pictures of that, and I'll show you how that actually works. But there is a calculation called cylinder boundaries, and until Vista, we had to have that. Now, Linux solved this problem. It's already been fixed, and Mac OS has already had it fixed. So those are not problems for those operating systems. Only Vista and Windows 7 have solved this problem. XP has not solved this problem, and you have to do different things with anything XP and older, which a lot of us are probably still using. A sector until 256 megs of NAND was 512 bytes. After 256 megs, they then went up in size so that they had less of a table to follow. So they had more space to actually store and more time to actually store and calculate the existing content. So we went to a 2K sector, a 4K sector, and an 8K sector, and probably 16 really soon. So we have a variation in sizes of sectors. The content's still being delivered to us logically, but there is another table that is now in between the data called a PBA to LBA table. LBAs basically are a sector. PBAs are physical block addresses. And so basically now all the content is hidden from us, and there's another table that says this used to be a value over here, but it's no longer this value over here, it's over here. And it can shuffle this content around on its own. And so you'll now have pointers that point to where these sectors exist. And then we have this other complication called blocks. The reason we have a complication with something called blocks is because you're used to a single sector being able to be erased or rewritten. But now it has a charge. It has electrons sitting in that cell. So therefore, you cannot write to it again. You have to erase it. And you cannot erase a single sector. You have to erase things on a grid. And the grid actually has to be a charged of 20 volts in order to actually release this content from a single sector. So it does not erase a single sector, it erases the entire block. So you actually have to get rid of multiple pieces of content. I'm going to show you what those numbers look like in just a second. The way that it erases this content is by opening the drain and allowing the electrons to escape. Now, you do not actually see little pieces of plastic popping up and light coming out and all this other stuff. But in the lab, back in 1984, when Dr. Fuji Masasuko was working on this, he had a partner who was in the lab who was working with him, and when they would actually go through trying to release this content and let it escape, it actually did flash. And so the other doctor said, hey, that looks like the flash from a Kodak camera. And that's where the name flash came from. And so flash has stuck with it ever since. That was its nickname back then. And that's why, because during its erase cycle, the electrons escape, and it does kind of have a charged value. Now, we don't see it. It dissipates differently now, but basically in the testing lab, that's primarily what it looked like. So, moving on. Now, this is where we're separating ourselves from hardware to software. Up till now, everything's been hardware. Everybody uses the same chips. Everybody has the same stuff. Basically, now we're looking at a process that runs that is a piece of software or firmware, and it is a function called wear leveling. And the theory here is that you have a USB thumb drive in your pocket, and on that USB thumb drive you have a PDF. And that PDF, you hardly ever edit. I mean, some people have editing software for a PDF, but generally speaking, PDFs are carried around as some sort of a reference material. But you have a Word document that maybe you edit it, and it changes. So why don't we swap the pieces that change with the pieces that don't change, and let's keep them all written at about the same level. Not only the content, but things that aren't content, blank space, spare sectors, devices, device area, all of the other content. So the entire area is virtualized, and the entire area is all swapped around. So all of the data, no matter what it is, including its spare space, is then swapped evenly all the time. And therefore, you can actually increase the amount of time that the device will live. And the marketing people will tell you some ridiculous amount, like 51 years, which is probably a lie. Who's going to be around to tell us that it didn't last that long? But generally speaking, you're looking at the difference between engineering and what marketing tells you. And the marketing stuff is all based on this fictional software stuff that's actually happening. And it's not about files. I know I have a file and I have a file name up there, but I want to make sure you understand your device doesn't know crap about your files. I don't care if it's a hard drive or a solid state drive. They don't know anything about your files. That's the job of your file system and your operating system, to deal with files and clusters. So it doesn't know. Basically, it's relying on the device to say, hey, this is free. This is a free bitmap. This is something else that happened. And we do have some recent changes, like trim is a new feature that's been added to solid-state drives. And trim is a firmware function that basically does two fundamental things, but the operating system also makes changes to itself based upon this. Trim was requested by Microsoft to the ATA Command Committee. The ATA Command Committee is where you can actually say, hey, hard drive, are you a solid-state drive? And it can say, yes, I am a solid-state drive. And therefore, the operating system can do a bunch of different things that it would not normally do to keep the device alive longer. The device, like for instance, as an example, Windows XP starts shuffling content around, basically doing defragmentation, moving files that are based on performance to the outside edge of the disk. It actually looks at it and says, hey, we know the outside edge of the disk is the lowest LBA number, the lowest sector count. Let's move that Word file that you were just using to the outside edge because you open it 75 times a day. So let's try to move that to the lowest number. On a solid-state drive, that means nothing. There is no such thing as a lowest number. It shuffles this content all over the disk. And every time you write to it unnecessarily, it will actually cause another death in another cell. So they want to turn that feature off. And there's a whole bunch of features that are turned off. Basically, Windows 7 is the only thing that supports trim. Windows XP does not support trim, and it will not support trim. They do not plan to add anything to it. So you will have some other things that will actually happen. One of the other things that Windows 7 also does is tells the file when it's been deleted to tell the device that it's been deleted to go ahead and delete it now. So in other words, it's not waiting for unallocated space to eventually be wiped by a garbage collection routine in the device. It says, go ahead and erase it now. You can now have it back. So I have free space on the device. The device functions differently. A solid-state drive will function differently full than it does when it's empty. When it is full and all the sectors are full, it has to use spare sectors in order to swap content around as it's being written to it. So if you want to diminish the time that it takes, erase other things earlier. And that's what one of the trim features does, basically, is say, now I can erase this content. But forensics people, how many people in here are forensics people? So like most of you. So in forensics, you'll also see other things that will disappear in Windows 7, like prefetch. Prefetch files will disappear, which you've been using for forever. You will no longer have slack space. That will disappear. Unallocated space will eventually go to 0. You won't see anything at all. The content will actually be blank. As soon as trim says, I'm done with this file and I've erased it, then it's not available anymore. And the device may actually have content stored in a cell somewhere, but you can't get to it. The device runs interference, and you can't access that data directly. So there is an impact there that's going to change, along with a number of other features that actually happen. Even in XP, even though XP doesn't have trim, its defrag process will actually cause the unallocated space and the slack space to go to 0. It eventually will be nothing in those locations. So just understand that there is some differences here with the intellectual property firmware leveling. You will actually have a process that is different from one manufacturer to another and how they handle the content. So Lion now supports trim. However, they have not told us what other features they turn off or turn on or do anything with. EXT 3.4 does not currently support trim unless it's been modified in the operating system. 4 does support trim, and the features can be turned on. I'm not sure all of the other operating system features that it diminishes, but ext4 by itself also makes a change to the metadata and how the metadata is stored so that it's more efficient. So there is some other features with the other operating systems that have already solved some of this with trim. So we're only looking at Windows 7. Even Vista doesn't support, which I'm sure all 6 people that own Vista are going to be disappointed about, but it does support trim. So you don't have to worry about it, only Windows 7. And going forward, that's the only other thing we have to deal with anyway. So, but that's the way it goes. Now, what this slide was about is basically on a hard drive, you can modify a particular sector or location. Not that the file that you open and edit does, because Word may make temporary files and then replace them or whatever. But most of you know at this point that with a hex editor, you can go in and edit a sector, and that sector, 525, will be the same when you come back to it. Right? Everybody good? That is not what happens on a solid-state drive. On a solid-state drive, you now have a charged value, and that sector or that set of sectors has content that's already stored in it. And so when you make a change, the device has to write it someplace else. When it writes it someplace else, understand this is when slack space disappears. This is when you have unallocated space that will disappear. But it will then take that content, write it to a new location, and then it will put the old one in what's called a garbage collection routine, and it will remove it from your access. Now the PBA to LBA table will then have it removed, and you do not have access to it. So I know what everybody's next question from a forensic standpoint usually is that, well, what if we desolder this chip and we go and look at it? Can we see the content there? Well, I want you to understand, first thing is, things are based upon sectors that now are not contiguous. So the content's not contiguous anymore. And in newer solid-state drives, in Generation 3, Generation 4, and possibly Generation 5 if we're crossing over into it, they now have added encryption and compression. And those two things then remove our ability to easily see contiguous data. So without the controller and understanding what the controller is, what the seed value was for the encryption, and people go, well, I didn't type in a password, so what's it encrypting? It already has a seed value. They are already using hardware encryption inline. So if you're using like Intel drives, Intel X25 or SandForce, those are all encrypted inline, even if you don't add a password. If you add a password, then you have a new salt. So therefore, now you have a new encryption process. And when you erase them, the process called secure erase, which some of you've seen arguments about at this point, secure erase, yeah? So secure erase in a hard drive means something real. In a solid state drive, it's completely fake. They're just stealing the name. It really shouldn't even be called that for secure erase. In a hard drive, what it means is you have a bad block on your hard drive. Everybody knows that as you're writing data, you have a bad block, right? The content was written in a sector. 512 was written. The device checks ECC. It says, oh, crap, something really bad happened here. Let's go to a new location, and let's write in a reserved location called the system area what was going to exist in this original bad block, and let's take a flag and let's point it to that. Everybody got that concept down, right? So 6 months later, you've now written new data, and new data is now in this reserved location because that's now replacing the original sector that used to be there at that 512. Everybody good with that? What's in the 512? What's in the old one? Whatever was there last. The first time that you wrote it that it was bad, that content still sits there. You understand that, right? So how many people use DBAN? Hey, so when you use DBAN, what does it erase? It erases the new redirected block, not the old original block. The old original block still got 512 bytes of data in it, random data, which you don't even know it was there. So let's say you send it to somebody who's got the proper equipment to clear the bad block list, which is called a G list. I now will see however many bad sectors that you had, and I will see the content that was in it. So if you're at the DoD or DOJ or you work for, RCMP or something like that, and you're selling a drive on eBay, that could be bad news. So you'll appear someday on. Anyway, just understand, this is also the same complication that happens with forensics people when they testify on the stand that they have indeed imaged the entire drive. When you say you've imaged the entire drive, you don't know. You have no idea. Unless you've got the right equipment, and there's only like 2 or 3 pieces of equipment that will tell you that the G list has content in it. You did not image all, even the user available area. There is a whole nother set of data that exists on the drive. Just because you got the user data and it matched an MD5, that's not accurate. That is not true. You did not image the entire area. Everybody good so far? That means everybody's lied.
When you
Yes, I'm glad you mentioned that. So the ATA secure erase, the reason I mentioned secure erase in the first place was that the secure erase function is actually an ATA command that was added by the Center for Magnetic Research and Recording, which actually goes track by track and ignores the redirected blocks. And it actually erases the original sector that had that 512 bytes of bad data in it. DBAN does not. DBAN does not do secure erase. So in those particular instances, you have to use the command. Not every hard drive supports it, but most hard drives currently do support it. But secure erase actually means I'm moving the head to a location on a track, and I am erasing it track by track, not sector by sector, erasing that original content. On solid-state drives, what they do instead is, remember this key that I talked about earlier, that it creates a key and it's encrypted? It just destroys the key. That's all it does. It destroys the key, and so no longer is there a way for you to decrypt what that content was originally. That content is now gone. And in some cases, the drives are now smart enough to know when you say format a drive or wipe a drive that you are asking to destroy all of the sectors or make one more write. So what it does, creates one sector that has 0 value and points all of them in the PBA to LBA table to one sector instead of all the sectors. The content still exists, but is it available to you? Not without some intervention, not without some physical access or desoldering and doing stuff. So I know I'm going a little off track here, but I want to make sure, because most of you forensics people, and I want to make sure that those were some concepts that you got down, because those are all myths with regards to how the content's stored in the head assembly in the bad block table, and most people don't know it. And I don't really want you testifying on the other side of me, because then I'll have to say, no, you didn't get all the user area. So anyway, let's talk about the numbers. Let's talk about what actually the layout is and what you're actually looking at as far as content goes. So basically, I've broken this down from the smallest so that you can actually see that what we're actually dealing here is our smallest writable unit is a sector. Now, a sector on a hard drive, 512 bytes. On a solid-state drive, not the case anymore. So in this particular situation, I only put a 2K sector. But now it's 2K, 4K, and 8K, and possibly 16K in the future. So whatever that size is the smallest writable unit. So basically, the device has to collect enough data to fill up those sectors in order for, or that content to fill up a sector. Then you have your smallest erasable unit. That is a factor of a numerical value based upon the purchase of the NAND chip. So in other words, when you're buying a NAND chip, you basically, as a manufacturer, have to say how big is the sector and how big is this block that I'm going to deal with. And so in that particular instance, what you're looking at, most of them are choosing 64. So what this means to you is that when you go to erase something, you take your value times the size of your sector, and that's how much the block has to charge in order to erase it. In this particular case, 2K times 64 is 128K. You would erase 128K at a time. So what you have is you have a street, and before anybody can move into that, everybody has to move out. So you got a block that 2-3 people bought a new house and moved off. Until all the other people move, no one new can move into that block, because that block has to be completely empty and erased, disinfected, before a new person can move in. That's really what we're looking at. Everybody good? So, as we start to break this down and we compare it to a hard drive, still today, pretty much, except for the Western Digital 4K drives, you're dealing with these sector sizes of 512 bytes. That's your smallest erasable, and that is also the smallest bad block. When you have a block that's bad on a hard drive, it marks 512 bytes, and that's it. But that is not the case when you're dealing with NAND. When you're dealing with NAND, you have your smallest writable unit is a sector. Your smallest erasable unit is that block size, where you're actually dealing, in this case, with a multiplier. And then, if there is any single cell that's bad in the entire block, then the entire thing is marked bad and no longer used. Now, this is where software comes in, and software can kind of modify this depending on some calculations. They have different things called write amplification and some other algorithms for trying to figure out where one thing may vary from another, where they may have some sectors they can still use and just ignore the bad ones. But traditionally speaking, on any of the existing solid-state drives up to the 3rd generation, it would mark the entire block bad. So if it was 256K, it would mark you bad. So all the other stuff is software tricks. Somebody trying to figure something else out. So unfortunately, on all of the classes any of you have ever had on how a hard drive stores data and how data is written and what a sector looks like is a lie. Everything's been a lie so far. This is what a sector actually looks like. And this sector, right here on a hard drive, is stored in a wave format. Basically, it's encoded, randomized, and Reed-Solomon algorithm was run through it, nullified, and then it has blank bytes in between. There's something called servo data, so that you can actually figure out where the track is, where the content is at that particular location. You have blanks as the head's going along. It still has address information. And one of the horrible things is that, how many people in here use Encase? How many of you have imaged with Encase, a hard drive? How about FTK imaging, DD imaging, right? Every time that you've had a bad sector, it pads it with zeros, right? So there's actually an error. The drive, every single sector, with identifying each one of these items, has an actual error code that goes with it. And it would tell you, ID not found, AMNF not found. There's all these markers that actually tell you what's wrong with your sector, and there's a possibility of reading out of the 512 bytes of data. If, let's say, 512, maybe 2 bytes is bad, whatever's left, you can still read. There's still a potential for reading that content and filling that space. It's somewhat of a little bit of a guess, which is probably one of the reasons why it's ignored at this point. But I'd rather have 510 bytes out of 512 bytes. What if ECC is wrong? I'd still like to have the content out of the 512 bytes. You can read that, and you can get this error. You just can't do it with those tools. Those tools don't help you at all. There is software that actually does, like MHDD, will tell you what those errors are. But none of the currently existing thousands of dollars of packages actually do that. Hardware, there is some hardware equipment that will. Anyway, just know that it's available. There's ways to get around it. This is what we're looking at with NAND and solid state. Basically, all this legacy stuff, you have to understand that the people who are making solid state drives now did not make hard drives. Those engineers did not come from this mechanical engineering background that hard drive manufacturers did, and they haven't had 30 or 40 years of learning. So what they're doing in solid state drives is getting rid of legacy. They're just saying, we don't need that stuff. That stuff doesn't mean anything to us. We don't need all these ATA commands. Let's get rid of most of them, and let's only do these 5. And there are problems that do occur as we go forward with this, as they're ignoring those things. And so understand that some of this data is just leaving us. So we don't have some of the diagnostics material. Labels on hard drives no longer make sense on solid state drives. You can't tell the same exact model and the same firmware from one to another, which you can with hard drives, but you can't with solid state. You know, your USB thumb drive, take one out of your pocket, look at it, and then go to the store and find one just like it. Good luck. You can't even find one that you can resolder that chip onto. It's almost impossible. You can actually have ones that have chips that are labeled exactly the same from one country to another country, completely different. Even though the numbers are exactly the same, the encryption algorithm used in the US may be different than the encryption algorithm used in Britain. And those two devices will not be the same, even though the numbers match. So you're kind of stuck with this whole process of trying to decode this content as we're moving forward. So you'll see that this stuff is taking a backseat and it's dying. So what is the difference when you're looking at a flash drive for a USB thumb drive versus a solid state drive? The main thing is, when you're looking at a flash USB memory stick, this device has no processor. It has no brain of its own. It is very reliant upon your operating system. It is relying upon a driver in order to do its job. When you plug this thing in, you'll actually see mass storage driver starts up on your machine. Firmware then is loaded, and then it will actually use your processor to do all of its work. It is a host-based processor device. It needs your CPU in order to do some of the work. So this is actually a layout from SanDisk called TrueFFS. And so as you can see, your file system then makes a request. It goes through all of these emulation layers and things that it's going to do before it talks to the flash memory. But this is all happening based upon device drivers and device services. So basically, when you're unplugging this device, even if you were to apply power to it, it really can't do anything. So if you could give it power, it still wouldn't do anything without your processor or without anything else able to manage it and handle it. That is not true of an SSD drive. And from a forensic standpoint, this is where a difference comes in. You plug in power into the device, it doesn't need to talk to your computer to do work. It's doing work as soon as it's got power. It has its own processor. And its processor then loads its firmware, and then it moves on from there, and it'll actually do all, this is what the definition of what it has to and what's the requirement from Intel for all solid-state drives to work plugged into one of their motherboards. And that's all NAND functions, all the block device calls, wear leveling, bad block management, erase cycles, garbage collection, ECC. There's a whole ton more of stuff that actually happens. And it manages and manipulates lists of content. So as we're looking at some of the content going forward and how differences between the hard drive and the solid state drive, even when we're dealing with firmware and things like that, here's some of the things that are different that I'll show you solid state in a minute, what the layout looks like and how it's actually managing it. But on a hard drive, we have something called a system area. Every single hard drive has a unique area that has something very similar to a mini OS running in it. When power is applied and the firmware kicks in, it'll actually go to the tables that are stored on the system area on the platters. It'll read tables and content from them, which include things that include data, as well as manipulations that are actually going to happen. This is some of the stuff that's actually stored on the platters. And I want you to really note one of the biggest things, because this is actually when we're dealing with data recovery, one of the most important things is the serial number. On older hard drives, some of the boards contained part of a model number or a serial number, but pretty much since 2003 or 2004, every drive has contained a serial number inside the system area. If you got a serial number from your drive, an actual true serial number that matches the label, then most people who are like, I'm going to repair my drive, should I replace the heads? Maybe something's wrong. If you received the serial number from your device, that is one sign that a head is good on your drive, that it was actually able to get partially through firmware and read content from the platter, and that you actually have a head that may be good. And this is where I see the do-it-yourselfers just kind of say, well, I ripped out the heads and I replaced them because I couldn't read anything. Well, they don't know what they've read or what they haven't read, but there are some system tables that actually give you this content. In these lists, this right here is your bad block list. These things are stored on the platters. So the P list is your primary list, and the G list is your grown list. The grown list is actually the bad block sectors that you're used to dealing with. But all of this stuff is basically disappearing. As we move forward, you'll see that some of the things that are legacy things in solid-state drives are just gone. This is utility block addressing. Utility block addressing is something that programmers use who are working on the hard drives to decide, hey, I need a bad block table and I need it to make it this big. And you can have one block table that you talk to as UBA1 and it be a variety of sectors. Those kind of things are disappearing. And in SSD drives, it looks completely different. So you will have some of that symbolic information, but most of it is all completely replaced with something else. So this is basically what's happening is you're taking all of your NAND, you're kind of soldering it all together, you're virtualizing the entire area, and then on this device, you will write device area, firmware, updates, all of your tables. You'll see a PBA to LBA table, LBA to PBA table. You'll have bad block lists, and then you'll finally have your user area. And what I want you to know is that all of this is wear leveled together. There is no difference in your user area in the wear leveling function. If you have spare sectors, all of this content is mixed up together. So this is like confetti. You just take all of your content, put it in a blender, make confetti, and then figure out where it all is when you're looking at the raw data. If you took the chips off and you tried to do something with it, it'd be impossible to read easily. And compression has now been added, and so has encryption. So complicated devices at this point. This is what's stopping us from doing what we used to do a year or 2 years ago by desoldering RAM or NAND and looking at it. So these things are taking a back seat and disappearing. Now, when we're looking at damaged ones, which is specifically what I do because I deal with the damaged content most of the time, I'll do things like I'll deal with a hard drive that may be in a forensics case. Maybe I'm not the investigator or the guy looking at it. I will recover it for another investigator as part of my commercial business and send that back to him. So I may have somebody in FBI who sends me a drive, I do a recovery, and I send him back an image. And so this is primarily what I'm dealing with. These are things that we are losing. On hard drives, we are able to do a lot of mechanical things. So we have tools that actually deal with disassembly of platters and to take those and move them to another system. This is a common thing that actually occurs. This is actually what I teach in my class. I teach the disassembly process for moving platters and head assemblies to another device when you've got something like a motor that's been burned out, or you've got board repair as an example. Soldering and desoldering and using infrared desoldering units to actually repair a board is a common process pretty much every day at this point. But these are all mechanical processes that solid state doesn't have. You're not ripping platters out or not doing any kind of changes to it. I made that look easy, by the way, in this animation. That's like a 2-hour process. Even this one by itself would take 45 minutes for you to do as an efficient person to actually get a drive realigned, get the head assembly back up, and get it running again, but with the proper equipment and the right stuff. And another one that we're using is we're losing board swap. Board swap, when you have a drive that sometimes the head won't read some data, we can actually do a board swap live. Like let one drive initialize, unsolder it, move it to another board, and we'll actually be able to read content. In this particular case, as we're moving into USB, all we can do is either look at desoldering the chips, reading the chips maybe in a ROM reader, or finding another compatible board and doing that. As well as the fact that in some cases now, we have to take this control chip with us. The control chip itself may have custom firmware, may have something in it that's necessary, so we've got to take these two memory components and the control chip. Now, I would say that most of the time, we try never to do this anymore. Now what we try to do is we try to repair the board itself. You have something that's on the board called the TVS chip. Basically, TVSs are transient voltage sensors. So you'll have a situation, and this is true of hard drives too. Most 3.5-inch hard drives have something called the TVS chip on them. The TVS chip will be a 5-volt and a 12-volt, and they're the first things to blow when you plug in a bad power supply or you get a brownout or something like that. And the symptom of it will be the device will do nothing. It will not spin up. You will not hear anything. Nothing will move. It'll actually act like it's dead. And if you took a meter and you read it, you would actually see that there is no response from the board whatsoever. Those are symptomatic of a transient voltage sensor going. You just have to find the two chips, and literally all you have to do is break them off. You don't have to find a new one and solder it back on or anything. They actually short in line, and so you can just remove those fuses. Just don't plug them back into the same power supply that they came from. That's a bad idea. So on a USB thumb drive, you also have transient voltage sensors, and so they'll look like this right here, but you need to know which ones there are. On a SanDisk, there are 5 of them. And so if you remove them in sequence and plug them in and test them one at a time, eventually you may get access to the device again just by removing those voltage sensors. That's all they do is short the device. They're fuses to protect the device. But nobody knows this, and they didn't give you a real good diagram about how to remove it. So nobody told you which ones they were. I have pictures of them. If somebody wants them, email me. I'll be glad to give you the pictures. This is also true of solid-state drives. We try to almost never try to go back and try to remove the RAM and try to read the NAND itself. We'll be looking for components that are broke. We will be looking for a component that is fried or a transient voltage sensor and things like that. You'd be surprised at how often it is something simple. It was just a matter of finding the one that was broke. In a lot of cases, you got to have a duplicate of the device in order to compare them or to resolder them. But at least it's easier than trying to read NAND. What you almost never do anymore, I've done this, I have done it. This is a nightmare. This is so easy to mess up. It's so easy to bend a chip. If you're going to do this, you have to have an infrared ball grid array desoldering unit. You cannot do this with standard soldering stuff at all. You need an infrared desoldering unit. Hot air sometimes will melt the boards or do something with it, so you can't do hot air desoldering in most cases either, especially on two-sided boards. So you actually have to try to break them down like that. So, am I on time or right at it? That's what I got. Questions? Everybody good? Yes, sir?
Do the NAND chips degrade over time?
Yes. So you have a couple of things that actually happen with NAND chips. One is you have a shelf life. If you store content on a, let's say you used to take a picture with a Kodak camera and you took that roll and you put it in your drawer. In 25 years, you may be able to still go and take that and have it developed. On solid-state devices, the electrons will dissipate over time, and generally you're looking at 7 to 10 years, the device will go blank. So if you have not used it, let's say you're working on a murder trial, one of the common things would be, I take all the device stuff, write it to this device, and blah, 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 put it in the safe. You may not see it for 10 years until that murder trial comes back up again when he's got an appeal or something like that in the U.S. Then in those cases, it's going to be device. The device is going to be blank. There's not going to be anything on it. So that's a partial answer. Obviously, with wear leveling.
I kind of meant the ability to write to them as well.
So they do degrade, eventually dying based on the write endurance process. So they do gradually degrade to the point that they cannot be written to anymore. And once that actually happens, the device will remove it from available space and call it a bad block. So, yes, sir?
Are the hybrid drives, like literally a hybrid between the two?
Yes, a hybrid drive basically, like for instance the Seagate ones, they just take 4 gigs of NAND and they solder it on the board, and basically it becomes a situation where you can have, say, the operating system booting off of it or partitioned into that. But yes, I don't really expect hybrid drives to survive or do much very long. Part of the problem is that originally hybrid drives had to have a driver in Microsoft's operating systems to be usable, and nobody else supported them in the other operating systems at all. So. And they're kind of ridiculous. I mean, we're really looking at a price cost change here as we're getting up to, 500 gigs of NAND versus a terabyte in a laptop. At this point, how many people care? I just don't think enough. But the other thing is that because of solid state drives, we now have up to 500 megabit per second throughput from a solid state drive, which we cannot even come close to talking to on a spinning disk. And so those are going to be the things that are just going to trump it right away. When you're looking at things where people say there's a hybrid drive, like you've heard, the iMac might have a hybrid drive in it. It's not hybrid. They remove the CD, they put in a solid state drive, and they put in a spinning disk, and they're not even one combination of a device at all. I just don't expect hybrid drives to survive over any period of time at all from that perspective. One other thing to note is that almost every piece of software that does encryption has a maximum limit between 40 and 50 megabit. So if you put that on a solid state drive, you've diminished your solid state drive to the performance of a spinning disk by using software encryption. So hardware encryption is a necessity when you're dealing with that. PGP and all those have an upper limit of 40, 48, 49 megabit, just because the formula can't produce faster speeds than that at that time. So you're looking at processor intense content. Yes, sir. So when you're dealing with imaging, there are specific tools that can image knowing damaged sectors and can. So there's one, DeepSpar is actually here in Canada. DeepSpar makes a tool that's called the Forensics Imager, and they also make another one called the DDI, the Deep Hard Disk Imager. Those all track the bad locations, bad space, things like that. So you can actually get that content back or do something else called the long read in order to read that content. Knowing those errors or repairing those errors. That's my best option. There's 2 or 3 others like the Ninja and several others, but I don't think they're as good as the DeepSpar Disk Imager.
That works on SSD?
No, he asked me on imaging. He didn't ask me specifically about SSD. They will work on SSD on the logical basis. They will not do anything special to repair or see anything with SSD. There is a tool that's called the PC3000 Flash that's made by Ace Labs. However, it's expecting you to actually read the NAND directly, and it has a ROM reader with it. So there is something called solutions that people are trying to come up with to actually reverse this process in a manual fashion, but you can't get around encryption. So 60% of the market is unreadable right now because of encryption. So right away, you're looking at all the ones that are SandForce OCZs and any of the ones that are using SandForce chips and SanDisk chips and Intel chips. Those 3 different platforms are all unreadable just using NAND right now. You cannot do anything without repairing it. Yes, sir? The only thing I can tell you, I talked to a guy from NASA. I had a guy in one of my classes that was from NASA, and the only time that radiation seemed to be a problem had to do with the solder itself. So for instance, they send a space shuttle into space. Solder is different on the space shuttle in space based on radiation and UV rays and things like that. Otherwise, demagnetizing tools and all those kind of things do nothing to these devices at all. So they've all been tested. There's no real problem. It's only when you're looking at ultraviolet rays and things that may do damage to the solder itself that physically does something. And of course, they've taken all the lead out of almost everything now. So you now have tin whiskers problem still. That tin whiskers will actually cause you devices that won't work in 3 weeks, or whatever it is. If nobody knows what tin whiskers are, look it up. It's really awesome. But basically, you need lead to counteract tin whiskers. And so the funny thing is the military won't even use a device that actually has the eco limit of lead in it, that you actually have to still put lead in the devices for military purposes. They're not consistent at all. Secure erase commands on hard drives, when they say they work, they do work. When they're on solid state drives, 30% of them don't work at all. Yeah, period. So you really have to test. You have to know your stuff. They're getting better, but they're not great. The secure erase commands are really weak when it comes to solid state.
What would you recommend for data sanitization?
Hammer. Hammer on data sanitation. That's what you need. You have to destroy the device, drill a hole in. I mean, these devices are cheap for the most part. We're not looking at $20,000 devices like we used to. If you don't want anybody to get your stuff back, because let's say today you can't get the content back from the NAND, that doesn't mean in 5 years that we haven't reverse engineered this process and it's easier to do the old stuff than it is to do the new stuff. So we may read your content buying it off of eBay. Could happen.
Is there any way to identify which manufacturers have good computer erasing?
There are a few magazine articles that have been trying to publish them or whatever, but you need to do your own independent testing, and then you really need to have a device that you can disassemble and read the ROMs and see what's actually left on them. But you actually have to go through the whole process manually yourself right now because you can't trust anybody. I have done some work for a few companies, some of them that like begin with an I, things like that, and there are faults. There are problems with them, but I've reported some of those, and some of those have been fixed. But you don't know until you've actually gone through it. But I've been hired to do some of that sometimes. Yeah.
Sounds like SSD is a nightmare when you have damage, but what about
Yeah.
a fully working device for forensics? Is it really any more difficult than a hard drive?
It is difficult from a forensic standpoint to recover content that the bad guy might not want you to get. So that's really the trick here, is that if you're doing bad stuff, then an SSD is great for you. So that's really what we're talking about, is that you're losing some content. Now, there's always something left behind. As you know, the registry has a tremendous amount of valuable stuff for us. And now, even trim and things like that aren't going to affect Lion's doing all our work for us on Mac OS. They're making snapshots and pictures, and they have a volume space for us of everything being duplicated. It's really nice. From a forensic standpoint, it's not great from an operating standpoint, but there's a lot of content that's there that's left behind that you don't normally get. I think people are waiting on us to escape. Thank you.